Good day. We talk about efficiency and heating of electrical machines in this lecture. Now, the key concepts we are going to cover are what is efficiency of a machine, what governs efficiency of an electrical machine, or sources of losses in machines, and the effect of heating on performance and service life of electrical machines, insulation types of electrical machines, issues related to application and applicable some reference to some of the standards. So the efficiency of a machine is defined as the output energy divided by input energy, or output power divided by input power, or in other words 1 minus losses divided by input energy. And obviously the smaller the losses, the higher the efficiency. Now what are the sources of losses? Now the electrical losses, there can be electrical losses which are load dependent. They are copper losses in the stator, copper losses in the rotor, and temperature also affect on that. And then losses at the brushes if there are any brushes in the machine, and then the iron losses, hysteresis and eddy current losses. Now at the brushes, if there are any brushes in the machine, there is a voltage drop of 0.8 to 1.3 roughly. And if there are any iron losses, that would be roughly fall within 0.5 to 20 kilowatts per kilogram of iron in the stator and the rotor. The mechanical losses, which are speed dependent, are at the bearings and brushes as friction loss and the windage loss. When the rotor rotates, there is some wind effect. So the windage loss. Now both these quantities are speed dependent. Sorry. What happens to the lost energy? Now most of the losses are converted into heat, and a small amount is converted into vibration and noise. But the bigger part is lost as heat, which itself is a problem because we need to figure out how this heat is going to be taken out of the machine. Otherwise, overheating can destroy the insulations of the windings and so on. The service life of electrical machines, if the machine operates within the operational limits, then the service life is determined by the bearings. If we do not exceed the operational limits in terms of voltage, current, torque, etc. Which means if we operate within those limits, then the first thing to fail will be the bearings, which is a mechanical failure. But again, the service life can also be affected by the environment of operation. For example, what sort of humidity that is present in the surrounding, and what sort of vibrations the machine is undergoing, what sort of acidity or oxidation taking place, acidity present or oxidation taking place. But when overloaded, that will lead to a loss of service life. Now mechanical load overload will damage definitely the bearings. Electrical overload will cause excessive heating internally, which in turn will lower the service life of insulation material. That's the direct impact of overcurrent. Service life of electrical equipment, usually the standard uh, acceptance is that the electrical equipment diminishes by half for each 10-degree increase in temperature. So that gives you a good idea about how will be the impact on excessive temperature on the machine. Now, that happens because of the degradation of the insulation of the windings, mainly in case of electrical machines. Now, these are the things that may affect the service life of an insulator. Definitely the time factor, high temperatures, humidity, chemicals, fungus, dust, rodents, ozone, uh, noxious gases, and vibration. So all these can affect the insulation. Depending on the insulation type, electrical machines are classified into different classes. An insulation type mainly um, relates to the level of temperature that it can withstand. Corresponds to maximum temperature that the insulation material could withstand. If it is class A insulation, it could withstand up to 105 degree centigrade. Class B 130, class F 155 degrees Celsius, class H 180 centigrade, class R 220 Celsius. Now AS2768, there could be a newer version of this one. Electrical insulation materials evaluation and classification is one of the standards that defines these things, and there is a table 6b in WILDI as well. Inorganic materials such as mica can withstand higher temperatures compared to organic materials such as paper, oil and polymer when it comes to insulations. And then the 1997 version of AS1359 gives rating and performance including intermediate operation and temperature rise for the insulations. Now the temperature rise, since insulation class refers to the absolute maximum temperature that the motor is subjected to, an electrical machine operating in colder climate could tolerate a larger temperature rise. Hence could operate with a higher loading without exceeding the design limit. So the environmental temperature also matters. Issue to consider in such application is to prevent moisture development due to freezing and condensation, because if the normal temperatures are um closer to the condensation of water and so on, vapor, then that could be a bigger problem for motors operating in such an environment, not the temperature rise. Hotspots method specifies a higher limit than average temperature method of measurement. Now nowadays most of these industries use this thermal imaging techniques in order to find out what sort of hotspots are available present in their electrical power network, and they sometimes get the thermal images of the electrical machines also. Now this one shows typical limits of some DC and AC industrial machines according to the insulation class. Now the first one shows this curve, first number 1 curve shows the maximum permissible temperature of the insulation to obtain reasonable service life. Now the second one shows the maximum permissible temperature using resistance method, and third one shows the limiting ambient temperature. So this gives you average temperature rise by resistance method, hotspot temperature rise by embedded thermocouple. So that this is an extract from the textbook, so you can read more on the textbook about this. And the issues related to applications, like different applications, for instance, high speed machines are smaller for the same output rating. Low speed machines are more costly to build. High speed machines can be used in combination with gearbox to achieve the same output rating and torque at a reduced cost because of these two reasons. If the machine is operating at higher speeds, then obviously you need lower torque to operate the machine at that speed. That's why you use gearboxes to get lower speeds at of higher torque. Larger machines are more efficient. Smaller overhead as a percentage, because if the machine is larger, your conductors are larger, losses are less, and so on. So again, more information is available in chapter 6. Now all these things gives rise to the need to standardize, which means we should have a common metric between manufacturers and customers. Now the increasing call for high efficiency and minimum energy efficiency standard can be found in this Australian standard 1359.5 in 2000. And methods of determining losses and efficiency can be found in 1359.102 part 1, 2 and 3. There could be updates of these ones. So in this short discussion we spoke about sources of losses in electrical machines, and then the effect of overloading which leads to overheating of electrical machines, and then classification of electrical machines in accordance with their insulation class, and then some of the Australian standards related to motor efficiency and insulation levels. So that ends this short lecture. Thank you.